So what are we talking about today? Today, we're going to talk about enumerating Weyl cones for Xi arrangements. Theoretically, some of these words should be familiar. This is joint research with Eleni Tsanaki out in Crete, in Greece. Well, let's kind of get started. Since I've missed the last 2.5 days, I don't know what has and has not been defined. Sorry. So we're going to start at the very, very basics as to notations and stuff. Hyperplanes, yay! So basic notation. So we're just setting H alpha K, just be a hyperplane with some root or some vector alpha, and some K translates potentially. So generally, if we're having 0 here, it's H alpha, and then S alpha is going to be the operation that reflects everything over this hyperplane. Root systems, I think most people have seen root systems here before, but we're going to be focusing on crystallographic root systems here. So this is where the Weyl group notion is coming from. So we have some set of vectors that is generating our hyperplane arrangement. So in essence, what we have is, so we have this set of vectors. Every vector is going to give us some reflection. We can decompose our vectors into 2 sets, a positive set and a negative set. They can also be further decomposed into simple roots. So simple roots basically generate the entire set of reflections, blah, 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 the entire set of roots. Also, my brain is not fully on. So if at any point I make a stupid banana, just be like, I think you meant X. And I'll be like, you're correct. Simple roots, and then W we're going to set as the Vial group. So the group generated by the set of reflections for a root system. So I think this should all be easy peasy, warm and breezy. So now we'll start with the main objects in our thing, arrangements. So Coxeter arrangement, these are going to be just the reflection arrangements. So they're just, you take some root system, you look at all the hyperplanes associated to it, that gives you a Coxeter arrangement. And then a Xi arrangement is basically going to be these Coxeter arrangements with every hyperplane, in addition, having a unit translate of 1. So in essence, that's generated through this K01. So we have basically 2 hyperplanes for every 1 reflection. So one thing that you'll see, I do a lot of examples. So let's see what this looks like. So here I have a root system in the kind of thin lines here. So I have 3 positive roots, 3 negative roots. This is my A2 root system. So coming from braid arrangement. And then here I have my 3 hyperplanes associated to this. So this is the Coxeter arrangement associated to A2. So what would happen if I now take these and shift them over by 1? I get the Xi arrangement. So these 3 additional hyperplanes here give me, in addition to the other 3, so all 6 hyperplanes give me the Xi arrangement itself. So we have 6 different hyperplanes, and this is the arrangement we're going to be working. Okay, so what we're going to do is we're going to look at these things called regions. So a region is basically, the idea is you look at your vector space, you have your hyperplane arrangement inside of it, you strip out the arrangement, and you're going to be left with connected components. That's going to be your regions. So here in particular, we're going to have 16 regions. So we have 1 here, this kind of triangular piece, a second one here, a third one here, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 different regions. And we're going to try to decompose these a little bit more. And we're going to decompose these into areas called Vial cones. So a Vial cone, so basically a cone in general is going to be an intersection of open half spaces of some of the hyperplanes. And a Vial cone is in particular going to be the intersection of open half spaces when we look at the Coxeter arrangement in particular. So what you'll notice is I've been keeping the Coxeter arrangement kind of bolded here, so we can kind of always keep track of where it is. So if we take intersection half spaces of the Coxeter arrangement, you'll see we'll end up getting 6 different potential cones. So like 6 different triangular areas. So we have 1 here, which I've highlighted in blue, a second one on top here, a third one that I've highlighted in blue, and then 3 more on the bottom. So these are basically the kind of pizza slices that we get from this. And the question becomes, well, how do we know how many regions are in each cone? Like, how do we enumerate these? How do we count these in a nice formulaic way? So these regions, or these cones in particular, there's one cone associated to every element in the Weyl group. So that's one way to index at least the cones. And so we're going to be working with those. And that's why these are called the Vial cones, because there's one for every element in the Vial group. So yeah, so the question is, how many regions are in each Vial cone? So to do this, we're going to take a step back and talk about some inversion sets and some post-set terminology. So inversion set, here I have defined the left inversion set. And basically what it is you take your negative roots, you act on it by some element, and then you see what roots become positive. And then those roots that are positive is your inversion set. So here, let's look at an example. If I look at the element TS, so I have TS here. I guess I should use the banana. If I have TS here, then I'm going to take my 3 negative roots, 1, 2, 3. I'm going to act on it by TS. So what I do first is I act on it by S. So I flipped everything over by S. So I'm left with these 3 roots, the ones pointing downwards. Then I'm going to act on it by T. So acting on it by the hyperplane T, I reflect over this hyperplane, and I'm left with these 3 roots. I'm left with exactly 2 positive roots, alpha T and alpha S plus alpha T. And that is my inversion set. So alpha T and alpha S plus alpha T. So that's how we're doing these inversion sets. Another thing we're going to need is what's called the root poset. So the root poset is just a nice little poset on the root system itself, where we have alpha is less than b if and only if beta minus alpha is some integer or like some linear combination of the simple roots, some positive linear combination. So here on the bottom, I have a Hasse diagram for the A2 root poset. So there's 3 elements in my root system, alpha S, or just the positive roots, alpha S, alpha T, and alpha S plus T. And you can kind of see when we play this game, for example, with alpha less than B. So we have alpha S less than alpha S plus alpha T. If I subtract alpha S from this, I'm left with alpha T, which does kind of work nicely. So we have a root poset. And then what we're going to do on this root poset is we're going to look at antichains. Now, an antichain is basically some finite collection of your elements such that any 2 are pairwise, they're incomparable elements. So in other words, if you're looking at the Hasse diagram, you don't have 2 elements above or below something else. That's all that's happening. So as an example, in this small little root poset we have here, there's 5 different antichains. So there's the empty set, so nothingness. There's 1 for each element. So you can take an antichain of 1 element. And then finally, the only kind of quote non-trivial one would be the alpha S, alpha T. So we take the 2 bottom elements in our root poset. Are there any questions so far? All good. Have you all seen all of this before? Is this all like, yes? Okay, fun. Welcome to lesson 101 from 3 days ago. Anyway, so we'll have fun. So last year, Galen and Christian actually published a result on enumerating these regions on the number of regions in a Vial cone. And in particular, they showed that if you have some Vial cones, so we'll denote the Vial cone by CW here, then in order to know how many regions there are, all you have to do is you count the number of antichains in the subposet of the root poset phi plus, so the root poset we had, but we restrict it to the positive roots without the right inversion set of that element. So as an example, so if I look at the Vial cone associated to ST, so here on the left-hand side, I have this Vial cone associated to ST. So what I have to do is I have to first remove all the elements that are in the opposite. So I look at NT, the inversion set of TS, left inversion set. I'm left with these 2. This is the one we saw from previous. So these two elements I remove from my root poset, so I have them X'd out. I'm left with exactly just one element. So I'm left with two antichains, and you can see there's two regions. So we see a kind of nice duality here. All right. So now the question is there some quote unquote nicer way to see this? And that's kind of the question me and Eleni were trying to answer. Is there some other way to see this that might make this a little more exciting? So to do this, we're actually going to jump into diagrams.
I did hear that.
Wait, what did I say? Oh, did I screw something up?
Not exciting enough, that's what you said.
Not exciting enough. Oh, I mean, Christian. I mean, it's pretty damn exciting. Like, look, that's a sexy theorem. That is one sexy theorem. Was it? You all try to cause drama. Listen, I'm already sick with the no.
Inner evil.
Evil. No, like anyway, we'll keep going. So we're gonna take these and we're gonna look at it in a different light. How's that? We're gonna look at them as diagrams instead. So these are coming from Xi. So basically the idea here is you take your root poset and you just twist. So if you twist your head sideways, you should basically see this diagram and the root poset should look almost identical. So like the alpha 1,3 here. I'm here. Where's the thingy? There. The alpha 1,3 is kind of this corner shape, and it's attached to these two. Yeah. So you have this nice little diagram thingy over here. This is a good part to talk about the shorthand notation that I'm started introducing here. When I have alpha ij, so like alpha 1,1, this is just the sum of all the simple roots. So alpha 1,1 is in fact just equal to alpha 1. It just that's it. Alpha 1,2 is alpha 1 plus alpha 2. Alpha 1,3 is alpha 1 plus alpha 2 plus alpha 3. All right. So this is type A. And it turns out, I need one more thing. Subdiagrams. So how do we relate diagrams to antichains? And this was again done by Xi. So basically what he did is he said, what we have to do is we cut out our diagram into two parts. And the left-hand part just has to be a subdiagram. And what he defines as a subdiagram is basically it's closed under going left and going up. In other words, if I have some box, every box to my left and every box above needs to also be in my subdiagram. And in essence, if you kind of think about this, what it does is it creates a path in your diagram where the kind of corner boxes are precisely the antichains, are precisely the elements of your antichain for your root poset. So this is the basic idea. And this is the idea we're going to be working with for the rest. So 3 and 95 basically said, here's the three diagrams you have. You have type A. You have this nice little young tableau kind of shape here, young diagram. In type B, you get a little more complicated in that it's no longer young, but it's similar-ish. And then in type D, it gets even more exciting in that you have these kind of middle row here. And the way to interpret this middle row is that you have actually one box on top of another box. So you kind of have two layers of boxes on top of one another. Oop. So that's basically where those things go. So we were talking about paths. So how do paths get in? So this is the kind of trivial part. Well, not trivial, but like the kind of easy part is we're just going to convert everything into paths. So instead of just having boxes, we're going to put all the vertical edges pointing up, all the horizontal edges pointing to the right, and that allows us to have paths. So it allows us to convert diagrams into digraphs, and we'll be using this in a minute. And then we can do the same thing for type B. Here, there's some slight differences in that some of these arrows are actually pointed to the left. And basically what we're doing here is we're creating, every path is going to be associated to a particular antichain. So it's literally going to be the paths that shape out the antichains or the subdiagrams. And the reason I'm stating this is because in type D, it actually gets complicated. So in type D, the graphs we get are no longer as trivial. And that's because this kind of middle shape here, there's no easy way to construct a path that keeps track of how many things you've had on one, like the top part or the bottom part. So you have to break apart your graph into a little more complicated notion here in order to get a type D kind of graph for your systems. Here, the dashed lines basically mean that there's no path between, there's no line. It's just there for visual purposes to kind of see these boxes. But other than that, that's the graph for type D. And so what it turns out is, so what we'll do is for every root, we'll associate a corner. So remember how I was saying we can kind of look at these corners for the paths. So for any alpha, we just let pi of alpha be the set of subpaths that go under and to the right of alpha. So if you kind of look at alpha 1, 2 here, we're going to consider this path here as the path associated to alpha 1, 2. In particular, I'm going to say it's a set of subpaths, because if we look at, for example, type D, we might have more than one box associated to any particular root. So I might have to take more than one collection of corners, but that's not too bad of a thing. So then the first thing we kind of showed is that all you have to do is you get a very similar result in that you can now associate these antichains to these paths. And since there's a bijection between these antichains and paths, you just need to figure out when you're avoiding these corners. So you look at all subpaths that avoid these corners, and that gives you precisely the number of regions in this Vial code. So in essence, it's almost identical to the theorem here. So there's a bijection between paths in gamma, which don't contain subpaths in pi of w. And here pi of w I'm taking as the union of all of the pi of alphas, where alpha is in the right inversion set. And then this is just a bijection with the antichains as given before. All right, so at this point, you're like, okay, well then, like, how does this help? You've just changed it from anti-chain problem to a path problem. And that is where fun things start. So we're going to talk about overlapping paths. So in essence, we're going to go into a little bit of graph theory. I don't actually know if this exists in graph theory or not. But in essence, we're going to say two paths overlap if either one of them is a subpath of another, or if kind of they overlap in the beginning and end stages of one another. So here, these two overlap. This one overlaps because the top one is the subpath of the bottom one. And then these two overlap because the first edge here coincides with the last edge here. So in other words, they kind of overlap in the beginning or end parts. But things that don't overlap that seem like they should is when they overlap on just the vertex. So if they overlap on just the vertex, we don't care. It has to overlap on an edge. And the second thing is if it overlaps only in the middle part. So if it overlaps in the middle, then we don't let that count either. It has to really overlap in like just that beginning and final part. And so what we then can do is we can actually count the number of paths using a determinantal formula. So we basically have that if you have a collection of non-overlapping paths, which basically means pairwise non-overlapping, no two overlap one another, then we just have this determinant formula for counting the number of paths. And then here, I think I forgot to mention, so I'll do it now. Basically what the F and the I is, F is going to be the final node vertex of your path, and then I is the initial vertex of that path. So in other words, we don't really even care about where the paths are. We just really care about the final and the beginning part of that path. Oh, and then I forgot to say it should also be acyclic. So the cool thing about this theorem is we can now combine it with the results by Andre in 1887. So now we're going back 3 centuries or 2 centuries. That basically looks at lattice path enumeration in Z2. And it basically says if we have something above the Z equals or X equals Y axis, then I have this binomial coefficient, kind of binomial subtraction kind of thing that basically tells me exactly how many paths are between these 2 points. So we can combine this with our previous thing to, in essence, get a nice result for type A. So for type A, what we do is we just take our lattice paths and we put them in a nice way so that it is always above the x equals y axis. So I have my starting point be 0, 1, my final point be basically as far as I need. And then I associate every corner to precisely the corner associated to the edges. So like alpha 2, 2 would go from 1, 2, 2, 2, 2, 3. And so that gives me a nice way to actually define exactly where these paths are. And then we can use this to basically very quickly calculate the number of paths or the number of regions. So we can kind of do this in a not so trivial example. So if we look at A5, so 5 dimensions, and I take a Coxeter element W, so I have these 5. I'm left with these 5 roots as my left inversion set. So these are going to associate to these 5 corners, and you can kind of basically see this 1, 1 is associated to the middle component for each one. So 3, 4 is 3, 4, 1, 3 is 1, 3. So it's very easy to kind of pick this up and see where it's supposed to be. So we have these corners. Visually, what these corners just represent are precisely these corners. So that's it. So this might seem like it's going to be some big, long, complicated thing, right? If we're trying to actually enumerate these, this might take a while. But we can just plug it into our determinant formula. This seems like hell, so don't look at this. This is just plugging in the numbers. Because then we put in Andre's theorem and we look at the binomials, and you can see most of them go to 0. So most of these terms go to 0. And then most of these we can actually just do by hand. So like, for example, 2 choose 3 is 0. 2 choose 1 is 2. 2 minus 0 is 2. So like doing these by hand, we're just left with this easy matrix where still we have a lot of zeros, and we're just left with 38. So it's kind of nice and fast in this regards. So we have similar things that we can do in type B, and then we're doing things for type D as well. But I think, yeah, so I think I'll stop here because I think it's supposed to be 20 minutes. So I think I'm over it. But maybe not. I don't know.
It's 30 minutes.
30 minutes.
25 plus 5. 25 for the top.
I was told 20. Okay, well, you all get 2 minutes extra. Yeah. I went fast at the end, so if there's questions near the end, feel free. Yeah. If you want, if there's no question, I do have more graphs. So this is the type G2 digraph.
Wait, we might have needed a second to formalize the question.
That's okay. That's okay. Take this is the time to formulate the questions. This is F4, so F4 gets very exciting. And then if you want a more complicated D, here's D5. So it's super fun, but it's formulaic. So like there's an actual description on how to do these in a formulaic way. I have a conjectural E6 that I'm waiting to go back to the computer to double check that it works. But there's a way to do this in E6, and then once E6 is done, 7 and 8 are basically nothing as well. So in my brain, this is like the way to see dict paths in other types in essence. Now we have actual paths we can go down. But yeah. Yeah.
Can you do something like this for CM?
That's the next question. Yeah. So the idea is to try to use this to figure out M-Shi arrangements to see what happens when we do things. I think we had okay results for type A, but we haven't sat and actually double checked that it actually works and stuff like that. So that's in the testing phases currently. So yeah, but that's the hope and the goal.
Oh, I wanted something similar as well.
Same answer. I will copy my answer and paste.
Never thought about it, Aram, but is when
Suppose you start in a chamber for W and you go up, into WS, some adjacent chamber.
Yeah.
Do the number of anti-chains always go up or can it go down?
The number of anti-chains, they should always go down. Wait, am I doing that right? The number of regions should go down. So the number of so the number of regions should go down. And so let me see if I go back far enough. So basically the idea is that whenever you hop over whenever you hop over a hyperplane, and this is the results that Galen and Christian had, whenever you hop over a hyperplane, you're basically getting rid of one hyperplane that you hopped over. So like, for example, if you hop over this one, you can now no longer get back to this one, right? Because you've now gone into the negative part for this, so you can never see the positive part of that. So in essence, every time you hop over a hyperplane, at least when you're increasing away, like if your length increases, then your number of regions decrease. If your length decreases, then your regions would increase. Yeah. So
In every chamber, you've got an entire effector for that, counting the anti-chains by cardinality.
I haven't looked at the F vector, but theoretically, yeah.
Can you compute that effector?
Oh, we haven't looked at it. So okay. Brain is having a fart. Remind me how the F vector works. So the F vector in this case is just counting not only the regions, but also like the sub-dimensional components, right?
You can the Narayana numbers are counting those anti-chains according to cardinality. And it's sort of like you've got a simplifical complex of anti-chains and just how many anti-chains there are of each size.
I wanna say there's something, but my brain is refusing to cooperate.
I'll ask you later.
We'll talk. Sorry.